Okay, so today let's talk about chain rule. Chain rule is very important in order to understand the total derivative of a function of several variables. So to start with, let's consider a function w, which says the function f, and it is a function of three variable terms x, y, and z. Not only that, the variables are themselves function of t. So say x is a function of t, y is a function of t, and z is a function of t. So what if I want to know the rate of change of w with respect to time? So I want to know the total derivative dw dt, but I want to know it in terms of the partial derivatives. So the general rule is you take the partial derivative of this function f, which is w, with respect to x, multiply by the partial derivative of x with respect to t. Then do the same thing, but this time do with respect to y, multiply by the partial derivative of y with respect to t, and finally do it with respect to z. One thing I want you to understand when I'm doing del x del t, del y del t, or del z del t, if you look at these functions, x is a function of t alone. There is only one independent variable. So your del x del t term, if you want, you can actually write it as dx dt. That's equal to the total derivative because I don't have more than one direction. Similarly, if I consider del y del t, I can easily write it as dy dt, and dz dt is going to be del z del t. Now, when I get to say that these are equal, the partial and the total derivative, if the variable is a function of one variable, like x is a function of t only, y is a function of t only, z is a function of t only. So let's use this concept in order to solve our problems. We're going to find dw dt, the total derivative of w with respect to t, but w is a function of two variables, x and y, whereas x is a function of only one variable t and y is a function of only one variable t. So you write down the formula, you say dw dt, because I have only two variables, I will call it del w del x times del x del t plus del w del y times del y del t. And then I do the derivative. Del w del x, well, sine y is constant, so I just get to say this is derivative of x, which is 1, times sine of y, times del x del t, which is derivative of x with respect to t, and that's e to the power t, plus del w del y, well, this time I'm doing derivative of w with respect to y, so x is constant, and derivative of sine y is cosine y. So I write x cosine y, and then I do del y del t, which is negative 1. So I get sine y, but remember y is pi minus t, and e to the power t times sine of pi minus t. So I want to write everything at the end in terms of t so that I can use the value t equal to 0. Plus x, well, what is x? X is e to the power t. And then you have negative 1. So cosine, first change the y by pi minus t, and then you will have to use this negative 1. So your final answer for the first question will be e to the power t sine of pi minus t, and then minus e to the power t cosine of pi minus t. So that has answered the question when we were wanting to know del w, dw dt. That is your answer. Now you're going to work out this entire thing, but I want to understand at the given value of t. So I'm going to find dw dt, but answer should be evaluated at t equal to 0. Well, let's see what we get. So this is going to be e to the power 0 sine of pi minus 0 minus e to the power 0 cosine of pi minus 0. So I get to say e to the power 0 is 1, so this is sine of pi, minus e to the power 0 is 1, so cosine of pi. Sine of pi is 0, cosine of pi is -1, so I get negative times negative a positive 1, and that's my final answer to the second question. It is 1. So we'll carry on to our next example, and remember our general chain rule formula. It depends on how many variables you have. If you have more than one variable, then write them as partial derivatives with respect to each of the variable and multiply by the partial derivative of that variable with respect to the time t. The next problem on page number 2 is a similar problem, but what we want to do with this one, we want to first use the chain rule, and then we want to evaluate the given function for t and do our regular total derivative. So let's do it step by step. First, w is a function of x and y, x is a function of t, y is a function of t. Find dw dt by using chain rule. So it's like the last one we have done. You will say dw dt, the total derivative, is equal to del w del x times del x del t plus del w del y times del y del t. Look at w, differentiate with respect to x, you get 1. Look at x, differentiate with respect to t, you get 3 e to the power 3t. Plus del w del y, we're differentiating with respect to y, so you get minus, and then 1 over y's derivative is minus 1 over y squared. So this is the derivative with respect to y, and then you do del y del t, which is 8 t to the power 7. Couple more steps. So I will write it as 3 e to the power 3t. Then minus times minus is a plus 1 over y squared. I'm going to change y by t to the power 8. Again, it will be t to the power 8 to the power 2 times 8 t to the power 7. So your final answer is going to be 3 e to the power 3t. If you look at the bottom, you have t to the power 16, t to the power 7 on top. So 8 stays on top, t to the power 7 and t to the power 16 cancels, gives you t to the power 9 on the bottom. So that's your chain rule answer for dw dt. So I'm going to write it, 3 e to the power 3t plus 8 over t to the power 9. The second process is doing the same problem, but this time converting w as a function of t before you differentiate. So write w as x is e to the power 3t minus 1 over y, so which is 1 over t to the power 8. Then start differentiating. So I can do the total derivative directly. dw dt will be equal to 3 e to the power 3t minus derivative of t to the power 8 is 8 over t to the power 9 with a minus. And if you are questioning why this is going to be the derivative, think about t to the power 8 as, or 1 over t to the power 8 rather, 1 over t to the power 8 as t to the power negative 8. So then you are taking the derivative on both sides. So using the power rule, you will get minus 8 t to the power minus 8 minus 1, which is minus 8 over t to the power positive 9. That's what I said. So you get dw dt equal to 3 e to the power 3t plus 8 over t to the power 9. And that is the same answer that I got using the chain rule. I'm going to just write it one more time and finish up this problem. So the next three problems, we're going to repeat the same work. So if you look at problem number 3, it is a function of 3 variables now, x, y, cosine of z. Where x is t, y is t to the power 6, z is arc cosine of t. Whenever you see this term arc cosine of t, you tell yourself the domain of this t is closed interval 0, 1. Otherwise, these problems are not going to work. So I will say t is always in closed interval 0, 1, as long as I'm talking about arc cosine or arc sine. Okay. So first, using chain rule, so I said dw dt, just keep in mind that you have 3 variables now. So you will write it as del w del x times del x del t plus del w del y times del y del t plus del w del z times del z del t. And I'm going to do them, all of them separately, del w del x. So you are differentiating x, so you get y cosine z. Those are the constant part. Del x del t is going to be 1. Del w del y similarly is going to be x cosine z. And del y del t will be 6 t to the power 5. Del w del z is going to be negative x times y sine z, because it is the derivative of cosine z alone. Del z del t is the derivative of arc cosine. Recall the formula is minus 1 over square root of 1 minus t squared. That's the derivative of arc cosine t. So what I get? One thing that I have to remember, I have to change everything in terms of t. So y was t to the power 6. So I'll say t to the power 6. Cosine of arc cosine of t, that's your cosine z times 1 plus x is t, again you have cosine of arc cosine of t times 6 t to the power 5. Then you have minus xy, x is t, y is t to the power 6, and I have sine of z. So what is sine of z? Think about, if arc cosine of t is equal to theta, then I get to say cosine of theta is equal to t. What is cosine? It is the adjacent side of the right angle triangle over the hypotenuse. That should be t, so why don't I write it as t over 1? Which helps me think of this value in the first quadrant. Remember this being theta. This is the adjacent side, and I will say that that's t. The hypotenuse by the arc cosine value is 1, and I'm interested in knowing how much is this side. Well, it's a right angle triangle, so this side squared plus t squared must be equal to 1 squared. So this side squared should be equal to 1 minus t squared. Then I take the square roots on both sides. I get the unknown side equal to square root of 1 minus t squared. And if you are thinking what happened to the absolute value, you were right. Now, if you look at this picture, see this height is a positive height. So absolute value of this unknown value will be the unknown value, the positive portion, and that should be square root of 1 minus t squared. So what I'm interested in knowing, if you see sine of z. So sine of z is arc cosine of t. But I said arc cosine of t is theta, so I'm trying to find out how much is sine theta. Well, sine theta is opposite side over hypotenuse. The opposite side we just found out is square root of 1 minus t squared. Hypotenuse is 1, so I will say that this is equal to square root of 1 minus t squared. Where this is going to help us, now we will go ahead. So we had x times y, and then we will say sine of z, which I just found out is equal to square root of 1 minus t squared. So I'll say square root of 1 minus t squared, that's sine of z, times negative 1 over square root of 1 minus t squared. And what is happening? This value, square root of 1 minus t squared, from the bottom and the top will cancel each other. So I will have a much more simplified version of it. So t to the power 6 times arc cosine and cosine are inverses, so you get t. Similarly, this one is t, so I get plus t times 6 t to the power 5 minus t to the power 7. So then I'm going to simplify my answers. So I will get t to the power 7 from the first one plus 6 t to the power 7 minus t to the power 7, and hence this is 6 t to the power 7. The answer to my question dw dt is going to be 6 t to the power 7. This is using the chain rule. How about now I convert the entire w in terms of t, and then start working with it. So I'm going to go ahead and say, remind myself, w is equal to x times y times arc cosine, it was cosine of z, and then input the values of x, y, and z in terms of t. So x is t, y is t to the power 6, cosine z is arc cosine of t. So you get t times t to the power 6 times cosine and arc cosine of t being inverses of each other will give you t. So you will get t to the power 8. And then finally, when I simplify this answer for dw dt, I will go ahead and get that is equal to 8 t to the power 7. So I already made a mistake and I can find it. So first and foremost, dw dt is 8 t to the power 7. That part is right, but then I forgot one other thing on the last part. So if you remember, this much, when I found t to the power 6 times t and the rest of it, t times 6 times t to the power 5, that is good. But think about the last term. It was minus here, and then you had a minus there, so minus times minus should make it a plus. And I completely ignored that, which I shouldn't have done. And so that should be plus t to the power 7. So you will get 8 t to the power 7 in your answer. So I'm going to write it one more time, and we'll be done with this problem. So plus 6 t to the power 7 and plus t to the power 7. So 8 t to the power 7. So both of them are 8 t to the power 7, and it matches. So answers my question. Okay, so let's go to our next problem. This one is asking you to find del w, del s, and del w, del t using the appropriate chain rule. And then each of these partial derivatives should be evaluated at s equal to -3 and t equal to 6. So let's see how we do these problems. So these problems are, I would say, relatively easier, because what you will do, you will first go ahead and write w. For example, w in this problem is y to the power 3 minus 6x squared y. Now I will do what? When I'm finding del w, del s, I will remind myself that in order to know the partial derivative of w with respect to s, I'm going to take the derivative of y cubed and x squared y with respect to s as well. So if you think of y cubed and you're trying to find the partial derivative of y cubed with respect to s, you will first derive y cubed with respect to y. So I will say that this is going to be 3y squared times, you will take the derivative of y with respect to s. So that will be del y del s. Then I do what? Then I look at my other term, which is minus 6x squared y, and I do the same thing. I say minus 6 is the constant. I first take the derivative of x squared, so I get 2 times x times, I say del x del s. And then I multiply the second term. So I'm using the product rule. This is first function times second function. The derivative of the first function is this much times the second function without any change. Then again repeat the same thing. It's minus 6. Now you are doing the derivative of the second function and keeping the first function fixed. So x squared is fixed. I do the derivative of the second function. So derivative of y is 1, and then I multiply del y del s. So the basic idea is pretty much similar to what we have been doing. What is the only change now? We are saying when I'm finding del w del s, I'm finding del of the y cubed function, but with respect to y, and multiplying it by del y del s. And Then I'm doing the same thing. I'm saying minus 6 times. I'm finding the del of the function x squared y with respect to y first and multiplying del y del s. And then I'm doing it one more time. I'm saying minus 6 times del of x squared y with respect to x times del x del s. So this is your basic idea. And I did not write it to start with because this is a little confusing to understand the problem in terms of the regular chain rule. So I'm going to take it off from here. I just wanted you to know that it's nothing other than the chain rule. So what is happening? I'm going to now simplify this thing. So del y del s, look at y. Y is, of course, a function of s. And